Hey there, Stat200. So this week we're going to be looking at probability, which tends to be one of the tougher topics of the course. So I've got a few more examples than usual, and as always, if you have any questions, please just give me a quick email or give me a call. Let's dive right in. So a soft drink company holds a contest in which a prize may be revealed on the inside of the bottle cap. The probability that each bottle cap reveals a prize is 0.2. And winning is independent from one bottle to the next. What is the probability that a customer must open 3 or more bottles before winning a prize? Alright. So, they have to open 3 or more, right? Well, what's the scenario in which that happens? So they could have, for example, so we'll call these bottle caps here, right? So we've got a bunch of bottle caps. Let's say these are being flipped over in order. Now the only instance in which they have to open 3 or more bottles is that they have to be a prize winner, right? So if they turn over the first one and it has a prize in it, that's not included. If they turn over the first one, there's no prize, and they turn over the second one, there is a prize, or I guess pop off the top, whatever, then again, they're not opening at least 3 or more, right? But in order for you to have to open 3 or more before winning a prize means that this one has to be a non-winner, and this one has to be a non-winner. Note that it says 3 or more, so it doesn't say anything about these over here. You know, you could have non-winner, 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 winner. Great. That's 3 or more bottles. Or you could have non-winner, non-winner, winner. Again, that's 3 or more, right? So all that really needs to happen is the first 2 bottle caps that you have to be non-winners. So what's the probability that your first 2 bottle caps are non-winners? Well, if the probability that they win is 0.2, the probability of non-winning is 0.8. So this has to be 0.8, this has to be 0.8. After that, it doesn't matter whether these are winners or non-winners, you've already opened 3 or more, right? And when we're using probability, and we're assuming that these are independent, see, probability of winning is independent from one bottle to the next, that means that if we want to kind of compound these probabilities, all we have to do is simply multiply them, right? So just a quick refresher. Here's the definition of independence. So the probability of event A and event B occurring is equal to the probability of A occurring multiplied by the probability of B occurring. If that's true, then the 2 events A and B are independent, right? So in this case, the probability, or A here in this instance, would be that the first cap is a non-winner, and B, the probability that the second cap is a non-winner. We're being told that that's independent, so that means that this is true. So in order to find the probability that this guy's a non-winner and this guy's a non-winner, all we have to do is multiply them together. Where do we see that here? Right here. 0.8 times 0.8 is 0.64. So the probability you have to open 3 or more bottles before winning a prize, 0.64 or 64%. Now why are some of these wrong? What are these describing? This one's describing, and you probably wouldn't choose this one, but this one's describing the probability of having 2 winners and then a non-winner, right? This one is probably what would trick most people. This is the probability of having a non-winner, and then a winner. But that's not the probability that a customer must open 3 or more. That's the probability that a customer wins on the 3rd bottle cap. That's a different thing. That's not the same thing. This is a customer must open exactly 3 bottles in this one. This one just says, well, didn't win on the first 2, so it's got to be 3 or more, right? That's why this guy's the answer. And then this one is trying to trick you up, because this one's saying, okay, you know, we win on this one, we win on this one, we lose on the 3rd. And those of you who read that go, no, that's not right, it's the opposite. So you might be tempted to say, oh, well, then I'll just subtract it from 1, and I'll get this probability. And also, I think the large number here really appeals to people. People like to hold on to the idea that winning something is really unlikely. And so a high probability of having to open 3 or more means it's really unlikely that you'll win. But it's not that bad. So just think through it logically. What does it mean? If you have to open 3 or more, it means that your first 2 are duds, right? Then all you have to do is find the probability that the first 2 are duds. After that, you're done. Don't have to think about anything else. That's a tricky one. This is like probably one of the trickiest questions you're going to find. So just stop, pause the video if you have to, go over it a few times. I'm showing you the answer here, and so just think about it. I think this really, really nails down, this kind of summarizes the concept of probability and independence. All right, next one. Students who live in the dorms at a college get free TV service in their rooms, but only receive 6 stations. On a certain evening, a student wants to watch TV, and the 6 stations are broadcasting separate shows on baseball, football, basketball, local news, national news, and international news. The student is too tired to check which channels the shows are playing on, so the student picks a channel at random. The 2 events F, which is the student watches football, and A, which is the student watches an athletic event, are they independent, mutually exclusive, each simple events, or none of the above? This is kind of a tough question. So, let's go back to that definition. I'm going to write it again because it's super important. If 2 events are independent, I'm going to use F and A here, then the probability of F and A occurring is equal to the probability of F occurring times the probability of A occurring. Let's think about that. So is that true? Well, the probability of a person watching football and an athletic event, since football is an athletic event, it's actually included. So this is an example where the probability of watching football and an athletic event is equal to the probability of simply watching football, right? Because if you're watching football, it is an athletic event. So the probability of the intersection of these two, remember if we have this, we call this a cap. If we have this cap in here, then that cap means both of these things are happening at the same time. If they're watching football and an athletic event, since athletic event includes football, it's just the probability of football. So, probability of watching football with 6 stations is 1 in 6, right? So this equals 1 over 6. But that means that they can't be independent, right? Because probability of football is 1 over 6. Probability of this is 1 over 6. The probability of watching an athletic event is not 1, right? It's 1/2. So if they were independent, it would be 1/6 times 1/2. This probability here would be equal to 1/12, right? You see what I mean there? So this is the golden rule for independence. And if you think about it logically, this is true in this case. Probability of watching football and an athletic event is just the probability of watching football. So therefore, can't be independent events. No, sir. All right. Disjoint or mutually exclusive events. Well, if you pick that apart, disjoint means apart, basically, and mutually exclusive means neither of them can happen with the other, right? They exclude each other. If football happens, you can't be watching an athletic event. If you're watching an athletic event, it can't be football. You see what I'm saying? If you write this down in probability notation, what that would mean is probability of football and an athletic event equals 0. Is that true? No, it's not true, because as we just discussed in the earlier part of this question, the probability of watching football and an athletic event is the same as the probability of watching football, which is equal to 1 in 6. 1 over 6. So, therefore, you know for sure the probability of watching football and watching an athletic event is not equal to 0. You see what I'm saying there? So therefore, it can't be a mutually exclusive event. It can't be disjoint events. They can't be disjoint events. Because it's possible for them to happen at the same time. If you're watching football, you're watching an athletic event. Boom. Happening at the same time. Alright, and then this one really confuses people. They're each simple events. And the best way I can think of to explain this is that there are no subgroups within each of these events. Right? So, football, a student watching football, that is a simple event because there's no subgroup within it. But the student watching an athletic event, that's not a simple event, and here's why. You could be watching an athletic event if you're watching baseball, football, or basketball. Right? So there's actually 3 simple events inside this one. But this one isn't a simple event. So they're not each simple events there. Which means our answer, which some might call a trick question answer, is none of the above. None of these is true. And this is a particularly tricky question because it really tests your knowledge of each of these terms. If you don't know any one of these, you choose it. You'd probably choose it by process of elimination. So, keep in mind what each of these is. If you want to have an independent event or 2 independent events, this has to be true. If they're disjoint, then this is true. If they're simple events, then there are no other events in the setup of the problem that are contained within those events. You see what I'm saying? Alright, let's move on. So, if the events A and B are mutually exclusive, let's just stop right there. If they're mutually exclusive, then this means what? This means that the probability of A and B occurring is equal to 0. Right? Then they must also be independent. Well, remember, independent means this, so let's write this down. This means mutually exclusive. And what does independent mean? That means the probability of event A and event B occurring. Oh no. Hang on there, sorry. Hit a button. Probability of A and B is the probability of A times the probability of B. And that's, I'm just going to shorten it here, I'm going to call it indep. Independent, right? Alright, well, as we saw in the problem above, if they're mutually exclusive, then they can't, they must not also be independent, right? We see that here. So it's something that should be noted here is that the problem does assume that both of these events have a probability of occurring. We're not talking about impossible events, right? So that's something that it's assuming. So we're going to keep that in our back pocket. So we know from this that they don't have to be independent. I mean, we learned that up here. Right? So, they don't have to be independent. Mutually exclusive don't have to be independent. Now let's talk about complements. So I think my best kind of visualization for complements and why, and the reasoning behind this one is, let's think about the possible rolls you could get if you roll a die. So you have 1 dot, you have 2 dots. Now I realize that this is not a perfect die here that I'm drawing, but I want to show you kind of the probabilities, right? So, the probability of getting a 1 and getting a 6 are not complements. However, they are mutually exclusive. You cannot roll, not on a normal die, you can't roll a 1 and also roll a 6 at the same time. with the same die. You see what I'm saying? So those are mutually exclusive. However, they're not complements of each other, right? The complement of rolling a 1 is not rolling a 6. The complement of rolling a 1 is rolling anything other than a 1. A 2, a 3, a 4, a 5, or a 6. Those are all complements of rolling a 1. Okay? So in that instance, you see, despite that these are mutually exclusive, they're not complements. So that one's not true. And in another example, let's look at the sample space of flipping a coin. We've got heads and tails. What's the complement of flipping a head? Getting a tail. What's the complement of getting a tail? Getting a head. So you see, they could be complements. So then this one's not true either. So we talked before about this. They don't have to be independent, right? And this makes sense. They don't have to be independent because they can't be independent. If you think about independent, the definition of independence in words instead of probability terms, the definition of independence is if you know the information about one event, then you still don't know anything at all about the other event happening. You still have no idea, right? That's the definition of independence. So if they are mutually exclusive events, for example, rolling a 1 and rolling a 6, or flipping a head or flipping a tail, right? Those are mutually exclusive events. If you roll a die and you know that it's not a 1, you know that what you rolled, you don't know what the number was, but a friend of yours looks over and says, well, it's definitely not a 1. Does that affect the probability that it's a 6? Well, before you knew that it wasn't a 1, your chances of getting a 6 were 1 in 6, right? But now your friend says, it's definitely not a 1. So then now, knowing that information, what's the chance of it being a 6? It's not 1 in 6 anymore, it's actually 1 in 5. You see what I'm saying? You know it's not this guy, but it could still be any of these 5 things. So the chance of it being a 6 now is 1 in 6, or sorry, 1 in 5. So they can't be independent. They can't, because if you know that one of them has or has not happened, then you know something about the other one. Similarly with flipping a coin. You flip a coin and your buddy says, well, it's not a head. Coins are easy. You'd be like, well, and then it's definitely a tail, right? So given some information about one of the events, you can actually learn something about the other event, the probability of the other event happening. So they can't be independent, you see? Now some of you might say, oh, well, what if one of the probabilities here is 0? And that's why I made a note before. The problem assumes that A and B both have a non-zero probability, that they're both possible events. And that's a good thing to assume because in this course, for sure, and likely in other probability courses, you're only really going to be talking about probabilities for possible events. It doesn't really make sense for you to discuss impossible events where the probability is 0. Why would you even bring probability up? Right? So, given that these two are possible, that they have a non-zero probability of occurring, if they're mutually exclusive, then they can't also be independent. You see that? Kind of a tricky concept. Let's move on. Cover some more. Okay, standard 52 card deck is shuffled. Side note, if you have a background where you're not really sure what a deck of cards consists of, I suggest looking it up on Wikipedia. I've had students in the past who have said, I've never played with cards before. I don't know. I don't know the suits, I don't know the colors, whatever. Please go to Wikipedia and just get a brief overview. We wrote this question assuming that it was pretty well known, but I have seen a few exceptions. So please, if you're unsure about what we're talking about when we're talking about a standard 52 card deck, please go read that. All right, back on topic. A standard 52 card deck is shuffled and 5 cards are picked without replacement from the top of the deck. The probability that the first 4 cards are a red suit, heart or diamond, and the last card is a black suit, which is a spade or club, is what? Now, really, 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 really important here is we're picking these without replacement. So we pick out a card and we're not going to put it back in the deck. All right? Second thing to assume, and very important assumption, especially when we're talking about 52 card deck and we're shuffling cards, is cards are independent. The probability of picking cards is independent. Okay? Now in this case, independence doesn't hold because we're doing it without replacement. So if you pick out a card and you're like, oh, it's the ace of diamonds. Well, now the ace of diamonds is out of there. And now you don't have 52 cards to pick from. Now you're picking from 51 cards. Okay? So I'm going to walk through this example and explain why this gets rid of your independence assumption and why it's important to know in other questions that cards are usually assumed to be independent. Okay. So the probability that the first 4 cards are a red suit. Let's talk about that first. So your first card, you're going to pick out of the 52 cards. You have all 52. Half of the deck is red, which is heart or diamond, and the other half is black, spade or club, right? So you have a 26 out of 52 chance of picking a red suit on the first card, right? Now these are independent, although these are not technically independent, but we can multiply these probabilities together because we're taking into account their change in probability. All right, second card. Probably the second card is also red. Well, now we don't have 26 red cards left. We have 25 red cards left. And how many total cards? Not 52, but 51. And we continue onwards. Now we only have 24 red cards and 50 cards total. And then we have 23 red cards. And, oh, no, not 50. Let's erase that. And now we have 49 cards left. Alright, so the probability that the first 4 cards are a red suit, you multiply these fractions together. And now the last card is a black suit. Well, there are 26 black cards remaining because we haven't actually taken any of those out. So we have 26 cards, but we're not drawing them out of 52 cards. We're drawing them out of 48. Right? This number right here, the denominator, continues to decrease as you remove cards. Right? There are just fewer cards in the deck now. The number of red cards decreases. And then finally, the number of black cards is 26 by the end. So what you need to do is multiply these together. Now the fastest way to do it, calculator. You could do this multiplying everything out, multiply this by this by this by this, multiply the numerators, multiply the denominators, divide it using long division. It's possible to do by hand, and I have done it by hand, but really not worth your time. So go to a calculator. Go find your calculator. I'm going to do the same. I'm going to multiply these out, and then I'll tell you what the answer is. So pause the video here and come back. Alright, so if you did this right, what you're going to see is this is going to be approximately equal to 0.0299, and then there's some extra digits. There's a 1, another 1, etc. You only need to go to 3 decimal places here. So this is the decimal place answer. To convert to percent, what do? Multiply by 100%. What's the answer? It's pretty obvious at this point. Right here. About 2.99%. So about a 3% chance that this would happen. Alright? And that's how it's going to work. Alright. And so what I was talking about before, when you're drawing without replacement, you see that drawing cards has an effect on the probability of subsequent draws, right? However, when you're talking about these cards in this kind of scenario where you're drawing cards out without replacement, you can assume that events between draws are independent. So drawing a red card out of a 52 card deck is independent of drawing a red card out of a 51 card deck, is independent from this scenario, independent from this, is independent from this. Okay? So that's important to note. They are independent, and that's why you can multiply them. Now, if I had said instead in the question with replacement, then it would be easy, right? It would just be 26 out of 50 divided by 52 times 26 out of 50, 26 divided by 52 times 26 out of 52 times 26 out of 52 times 26 out of 52. Or, equivalently, you could be 1 half times 1 half times 1 half times 1 half times 1 half, which is 1/32, which is slightly different from this answer, but not by much. Alright, if you have any questions on that one, please let me know. Let's move on to the next one. 4 students' names, including yours, are written on separate slips of paper and placed in a box. The teacher randomly draws 2 names without replacement. What is the probability that the paper with your name on it will be the second one drawn? Alright, well, if it's the second one drawn, that means the first drawn slip of paper does not have your name on it. So what's the probability that the first one does not have your name on it? Well, there are 4 students' names, including yours. So the probability that the first one does not have your name on it is 3 divided by 4. And the second one, the probability that the second one drawn has your name on it is now 1 out of 3, right? Now, are these events independent? Can you multiply them together? Yes, you can. Because once you have the scenario changes here. What's the probability of not choosing your name out of a 4, with a 1 in 4 chance? What's the probability of choosing your name when you have a 1 in 3 chance? These are independent events. And so you can multiply them together. And so if you remember, multiplying this one's really easy because you can cancel. So this 3 cancels with this 3, leaving us with what? Leaving us with a simple answer. 1/4, right? And there's that answer option right there. Don't get caught up in what the probability is on the second one. It's what's the probability that your name is on the second paper drawn. Some people get confused and they think, oh, you mean once you've drawn the first one, what's the probability that it's on the second one? No, that's not what I'm saying. I'm not saying once you've drawn the first one. I'm saying not knowing anything. And your teacher, the teacher is randomly selecting names. What's the chance that yours is the second one drawn? 1 in 4. Okay? Let's move on. Whoa, that's stuck with it. That's weird. Alright. See if I can get rid of that. I can't. Okay, well, oh well. A student is randomly selected from a large college, like Penn State. Define the following events. C is the probability that, or the event that the student owns a cell phone, and I is that a student owns an iPod. Now I know that we still have that, but a lot of people just have the phone because it's a smartphone. It's a slightly outdated question. So suppose you know that your friend's sister, who attends the college, owns a cell phone, and you're wondering what would be the chance that she also owns an iPod. What type of probability would this be? Well, is the probability that somebody owns a phone and an iPod independent? Probably not, right? I wouldn't expect that it would be independent. First off, if you have somebody who has not a lot of money, for example, and you find out that they don't have a cell phone, there's probably a pretty good chance that they also don't have an iPod. If you do a flip side, if you have a wealthy student who owns an iPod, you'd probably be willing to bet that they also have a cell phone. Right? So they're likely not independent. Are they dependent events? Maybe, but that's actually not what this question is asking. This question is saying, you already know that your friend's sister owns a cell phone. So if we write this in probability notation, we already know that she owns a cell phone. We know that already. We want to know what the probability is, given that she has a cell phone, that she also has an iPod. Now, when you already have a piece of information and you're looking at the probability given this piece of information, you already have some kind of information in there, that is a conditional probability. Right? So again, we're kind of talking about dependent events, but this isn't really what we're looking at. Dependent and independent doesn't really touch on prior information. Right? The prior information in this case is we know that this sister has a cell phone. So these are not really in use here. Probability of disjoint events, definitely not true. Because it's not impossible for a student to own a cell phone and an iPod. That's what a disjoint event would be in that case. So it's definitely not that. So it's a conditional probability. And the best way to remember that is, do you have prior information? Do you have information going in before you look at probability? In this case, you know that your friend's sister owns a cell phone. And you want to know, since you know this, you want to know the probability that she has an iPod as well. That's a conditional probability. Okay? There's a condition. Let's move it on. Okay. There we go. I'm not sure if this will show up on the video, but I have a piece of my text is sticking to the slide, which is strange, but just ignore it, I guess. Alright, so let's read this question. Alright, a student doing an internship at a large research firm collected the following data, representing all the studies the firm had conducted over the past 3 years. To find the events E, the study was an experiment, U, the study used randomization, and R, the study was a retrospective observational study. Which of the following sets of events are disjoint? So if you read the section on how we design studies, you would know that, or you would remember that an experiment is kind of the opposite of an observational study, right? So that kind of makes it really easy for you if you can remember that. You can use randomization in both an experiment and retrospective observational studies. That's doable, but you can't have an experiment that's also a retrospective observational study. So therefore, this is kind of the easiest one to classify, is just to say, well, what's disjoint? It can't be both E and R at the same time. So hold on a second. My program's acting up. There we go. So E and R can't happen at the same time. Therefore, E and R are the ones that are disjoint. These other combinations can actually happen at the same time. Alright, moving on. Michael wants to take French or Spanish or both, but classes are closed, and he must apply and get accepted to be allowed to enroll in a language class. He has a 50% chance of being admitted to French, a 50% chance of being admitted to Spanish, and a 20% chance of being admitted to both French and Spanish. If he applies to both French and Spanish, the probability that he will be enrolled in either French or Spanish, or possibly both, is what? So this is looking for, in probability notation, this is the probability that he gets accepted into French or Spanish. Now, I'm trying to make that more, they call this the cup. So before I told you this symbol here is the cap. this symbol is the cup. So the probability that he is in French or Spanish, well, if you remember how to show the probability for a union, now this is a union, it's a union symbol, looks like a U, just remember that. You do the probability of F occurring plus the probability of S occurring, and then you subtract the probability of both occurring, the intersection. So you subtract the probability of F and S. So in this case, the probability of being accepted to French, 0.5, plus the probability of being accepted to Spanish, 0.5, minus the probability of being accepted into both, 0.2, which is going to be equal to 0.8. Now you can simply remember that formula, or you can think about it logically. If we have, I like to think of this in terms of Venn diagrams. So I'm going to maybe move this slide up a little. Here we go. And I'm going to draw a simple Venn diagram. So here we have the probability that he gets accepted into French. Here's the probability he gets accepted into Spanish. And then, of course, if you're familiar with Venn diagrams, this part here is the probability that he gets accepted into both, right? Now, if we add these, if we want to know the probability of being in French or Spanish, that means we're looking at the total area of these intersecting circles, right? So we add this circle's area and this circle's area, but you notice when we do that, this actually gets double counted, right? This is included in the F circle as well as the S circle. So rather than counting it twice, we're only going to count it one time, which is why we're going to subtract this probability. See what I mean? Alright, so that is where that comes from intuitively. So there's that 80%. There's the answer. And finally, that's our last problem. That'll about do it for this week. Now there is a lot in here, and I know it's challenging. Please feel free to send me an email, give me a call, whatever you need to do to make sure you iron these out, because we will be coming back and revisiting these. We won't be doing it in as much depth, but it is something that you should know, and it will be on the midterm and the final. So take a close look, review this video if you have to, send me questions. You should do those extra questions on MyStatLab. Just make sure you really you've got this down. If you have any questions, please let me know. Otherwise, have a great week. Good luck on all those assessments, okay?